Moving average and exponential smoothing models in supply chain analytics. Learn how to forecast product demand using moving average and exponential smoothing. These models help businesses predict future demand when recent trends and seasonality matter. We will use real retail sales data to build, visualize, and evaluate these models. By the end, you will know how to improve inventory planning and reduce operational risks. Running the cell now. We import pandas to handle and analyze supply chain data. NumPy is used for numerical calculations that may be required for moving averages. Matplotlib allows us to visualize the demand trends and model performance. Importing warnings lets us suppress unnecessary output for cleaner results. Here, we ignore library warnings to keep our notebook readable. Running the cell now. Understanding our operational dataset. We will use historical retail demand data from a real UK online retailer. Each row is a transaction, with date, product ID, and quantity sold. It is common to trip up on date parsing or aggregating multiple sales correctly. Make sure you group data by both product and date for time series analysis. Running the cell now. Our goal in this cell is to load real retail store item data so we can build forecasting models. We are loading UK online retail demand data from the UCI repository. We specify the correct sheet to match the fiscal year of the sales records. We parse invoice date to date time so we can group demand by day later. Parsing dates ahead of time avoids future errors in resampling and grouping. This print statement displays the dataset dimensions to confirm successful load. Previewing the first few rows helps us quickly check the structure and columns before analysis. Running the cell now. The dataset contains over 540,000 transaction rows with 8 key columns, including the parsed invoice date, product IDs, stock code, and quantities sold. Notice the data combines multiple items per invoice with timestamps, highlighting the need to group by both product and date for accurate demand aggregation in our time series analysis. Now, let us make sure our data only contains actual customer sales, not cancelled or erroneous records. We filter out transactions where quantity sold is not positive, removing likely errors. Invoices starting with CE are cancellations, so we exclude those as well. After cleaning, we display the new data size to confirm only real sales remain. Running the cell now. This output shows that after removing cancellations and erroneous transactions, the dataset contains 531,286 valid rows and 8 columns. Noticing this reduction confirms the cleaning step is effective to keep only positive sales quantities and eliminate cancelled orders, which is crucial before any accurate time series grouping by product and date. In large datasets, we often start by analyzing the highest selling product to simplify forecasting. We identify the stock code of the most frequently sold product in our dataset. Now we filter the data frame to only include rows for this item. Let us print which product code we selected for all our forecasting work. Running the cell now. The output shows we've identified product 85123A as the most frequently sold item in our dataset. This step narrows our focus to one product, which is crucial for clean, accurate time series analysis by preventing mixed data from multiple products. Notice how selecting the top-selling product helps us simplify and deepen our understanding of its sales patterns over time. Forecasting needs data with a consistent time step. We will create a daily demand series for our product. First, we group the product's sales by invoice date and sum the quantities for each day. This aggregation step collapses all same-day sales into a single number. Rename the result for clarity. These numbers represent total daily sales. Resample as a daily series, filling missing dates with 0 sales to maintain time continuity. We print the first few days to confirm our time index sales data looks correct. Running the cell now. This output shows the daily total sales for one product, with dates as the index and sales quantities summed per day. Notice how missing dates, like December 4th, have been filled with 0, ensuring a continuous daily time series. This step is crucial for accurate time series analysis, preventing gaps that could skew trends or forecasts. Let us visualize demand to spot trends and irregularities before modeling. Set the plot size wide enough for monthly or yearly retail cycles to show up. Plot the sales series as points and lines for clearer visibility of sharp drops or spikes. Set the plot title to describe exactly what we are looking at, daily sales for our product. Label the x-axis with date for clarity. Label the y-axis with unit sold to eliminate confusion. Display the demand trend plot, which is the foundation for forecasting business decisions. Running the cell now. This line plot shows the daily sales trend for a specific product, highlighting fluctuations in demand over time. Notice how grouping by both date and product allows us to visualize sales patterns accurately, avoiding aggregation errors. This helps us understand seasonality or irregular spikes, crucial for inventory planning and demand forecasting. Practice, try plotting weekly totals for comparison. Are there visible time patterns? Beginner example 1, 7-day simple moving average. The simple moving average forecasts demand by averaging the last n days. In supply chains, this method smooths out random fluctuations. A 7-day average helps plan weekly replenishment cycles. Running the cell now. We apply a simple moving average to reduce daily volatility and get a sense of underlying demand trends. This line calculates a rolling mean over the last 7 days for each date. We create a wide plot for clear visualization of both real and smooth demand. Plot actual daily sales for reference. Overlay the 7-day moving average to observe the smoothing effect. Add a legend to identify series. Give the plot a descriptive title so operational teams understand what is shown. Show the chart comparing actual sales with the rolling average. Running the cell now. The plot shows daily sales with a clear line of the 7-day simple moving average smoothing out short-term fluctuations. Notice how the moving average curve is less jagged, highlighting the overall trend and making it easier to plan weekly inventory replenishment. This visual confirms the effectiveness of the 7-day window in reducing noise in demand data. Beginner example 2, 14-day moving average. Extending the window to 14 days further smooths out short-term noise. Longer windows are useful when seasonal patterns occur over bi-weekly cycles. Running the cell now. A 14-day average is often useful for retail periods that span pay cycles or alternate weeks. Here, we calculate a rolling 14-day mean as a more conservative forecast. This creates a series where each value is the average of the previous 2 weeks. Plot the actual daily sales first as before. Overlay the 14-day moving average for comparison in a different color. Add a legend so users can distinguish each forecast line. Provide an informative title for the new window size. Show the overall effect of smoothing with a longer period. Running the cell now. The plot shows the daily sales data with a much smoother orange line representing the 14-day moving average, which reduces daily fluctuations more than shorter windows. Notice how this longer window captures broader trends and seasonal patterns that might occur every 2 weeks, aligning with the lesson's intent to demonstrate how extending the moving average window helps reveal underlying trends by filtering out short-term noise. Question: what might be a risk of using too long or too short a window for moving averages? Beginner example 3, moving average as next day forecast. In practice, tomorrow's sales are unknown, we must use only past data to predict. We can shift the moving average result forward by 1 day to make a true operational forecast. Running the cell now. True forecasts should not peak at future values. Here we shift our average to avoid information leakage. Shift the rolling average forward to align with the period we are predicting, not the period just measured. Start with a wide plot as before. Draw actual sales for context. Draw the shifted forecast as a dashed line to highlight it as a prediction. Include a legend for clarity. Give a precise title so operations teams know it is a shifted, actionable forecast. Display the plot comparing reality to the lagged forecast. Running the cell now. This plot shows actual daily sales alongside the 7-day moving average shifted forward by 1 day to serve as a next-day forecast. Notice how the forecast line always lags behind the actual sales by 1 day, reflecting the realistic scenario where only past data informs tomorrow's prediction. This shift ensures our moving average is an operational forecast, aligning with the lesson's goal to use only available historical data for prediction. Intermediate Example 1. Evaluating forecast accuracy. Supply chain managers need to know how accurate their forecasts are. Let us calculate the mean absolute error, MAE, for our shifted moving average forecast. Running the cell now. Accurate metrics help operations teams improve stock levels and reduce wasted inventory. Here, we start MAE calculation after the minimum window so that all forecasts have enough prior data. We compute the mean of the absolute value of errors between actual sales and predicted values. Print out the forecast's mean absolute error in units, which tells us the typical mistake size. Running the cell now. The output shows that the mean absolute error, MAE, of 120.07 units per day quantifies the average deviation between actual daily sales and our 7-day moving average forecast. This numeric value is key for supply chain managers to understand how closely the forecast tracks real demand, highlighting areas for potential improvement in accuracy. Prompt: how might the cost of an error be different for perishable goods versus electronics? If you are interested in more industry examples, check out the Operations Analytics playlist on YouTube. Intermediate Example 2. Simple Exponential Smoothing Forecast. Exponential smoothing weighs recent sales more heavily than older data. This method is effective when demand levels shift but there is little seasonality. Running the cell now. Exponential smoothing helps respond to recent changes in demand more quickly than moving averages. Import the simple EXP smoothing model from stats models for exponential forecasting. Specify a smoothing factor alpha of 0.3, giving more weight to recent periods. Fit the model and collect the fitted values as our daily forecast. We shift the forecast by 1 to avoid using future values, making it a real operational tool. Make a clear, wide plot for visual comparison. Include the raw actual sales. Plot the exponential smoothing forecast as a dashed line in green. Add a legend for reference. Clearly label the plot with the method and smoothing parameter used. Show the comparison of simple exponential smoothing against actual sales data. Running the cell now. Here we see the actual daily sales plotted alongside the simple exponential smoothing forecast with alpha set to 0.3. Notice how the forecast line smooths out short-term fluctuations by weighting recent sales more heavily, resulting in a less jagged but responsive trend. This demonstrates how exponential smoothing captures shifts in demand without overreacting to noise, fitting our lesson's goal of modeling changing demand levels with minimal seasonality. Let us check if exponential smoothing gives a more accurate forecast than a moving average for our retail data. We skip the very first value, as it may be undefined due to shifting. Calculate the mean absolute error for exponential smoothing forecast. Print the typical daily error in units for easy operational benchmarking. Running the cell now. This output shows the mean absolute error, MAE, of 123.81 units per day, quantifying how closely the exponential smoothing forecast matches the actual daily sales data. Notice that a lower MAE indicates better accuracy, reflecting how well this method adapts to recent changes in demand without overfitting to old data. This helps us evaluate the effectiveness of exponential smoothing for forecasting dynamic sales patterns. Intermediate Example 3. Parameter tuning for exponential smoothing. Tuning alpha changes the model's sensitivity to recent changes. Supply chain planners must choose alpha based on how stable or volatile demand is. Running the cell now. We test multiple smoothing rates to find the best operational setting for stable forecasting. Initialize a list of store error metrics for each value of alpha. Set a range of smoothing parameters from 0.1 to 0.9. For each alpha, fit a separate exponential smoothing model. Fit the model for each alpha value to see how the error changes. Generate a next-day forecast as before. Compute mean absolute error for each separate forecast. Store the MAE result for plotting. Collect all errors for visualization. Make a plot of MAE against the smoothing parameter. Label the x-axis with alpha values. Label the y-axis as mean absolute error for operational clarity. Give a descriptive plot title showing what we are comparing. Show the relationship so planners can see the trade-off between responsiveness and volatility. Running the cell now. This plot shows how the mean absolute error, MAE, changes as we adjust the alpha parameter in exponential smoothing. Notice the curved trend indicating that certain alpha values minimize forecast error, helping supply chain planners select an alpha that balances responsiveness to demand changes with stability. This visualization directly supports tuning alpha to improve forecast accuracy based on demand volatility. Try coding. Does a higher alpha always reduce error in this dataset? Why or why not? Advanced Example 1, Operationalizing Forecasts, Weekly Ordering. Supply teams order stock in batches, often weekly. Aggregate your daily forecast to generate weekly order recommendations. Running the cell now. Businesses rarely place orders daily. Here, we simulate weekly orders based on daily forecasts. Sum the daily forecasts for each week to get forecasted weekly orders. Sum the observed daily sales for actual weekly demand for comparison. Initialize a large plot for weekly cycles. Plot actual weekly sales to show what needed to be supplied. Overlay weekly forecasted values to compare planning accuracy. The plot title highlights that we are comparing real and predicted supply needs for weekly orders. The x-axis is labeled by week. The y-axis is labeled as number of units, suitable for supply chain managers. Add a legend to distinguish between actual and forecast values. Display the plot so planners can see forecast alignment for batch orders. Running the cell now. The plot shows weekly aggregated sales and forecasted demand, highlighting their overall alignment and trends over time. Notice how summing daily data into weekly totals smooths out daily fluctuations, making it easier for supply teams to plan batch orders effectively. This aggregation is crucial for operationalizing forecasts to match the typical weekly ordering cadence. Advanced Example 2, Exponential Smoothing with Automated Alpha Selection. Manually tuning alpha is time-consuming in practice. Let us fit exponential smoothing with the optimized parameter. This is commonly done in business forecasting tools. Running the cell now. In production systems, businesses use libraries that select alpha for the lowest forecast error automatically. Fit the simple exponential smoothing model and let the software tune alpha for us. Retrieve the fitted values as our one-day ahead forecast. The selected alpha parameter is extracted for reporting. Compute mean absolute error for this optimal forecast. Print out the selected alpha and the associated error so teams can benchmark performance easily. Running the cell now. The output shows the optimized smoothing parameter alpha selected by the model as 0.05, indicating a relatively low weight on recent observations for smoothing. The MAE of 120.26 quantifies the average error between the one-step forecasts and actual daily sales, reflecting the fit quality. This demonstrates how automated alpha tuning efficiently finds a smoothing level that balances responsiveness and stability without manual trial and error. Let us see if automatic tuning provides a visibly better forecast line for our product's demand. Begin a plot to compare actual versus optimized forecast. Draw the daily actual sales as background reference. Overlay the automated exponential smoothing forecast as a dashed red line. Show the legend so viewers know which curve is which. Mention the selected alpha value in the plot title for transparency. Display the final optimized forecast process for visual evaluation. Running the cell now. The plot compares actual daily sales to the forecast generated by exponential smoothing using the automatically selected alpha. Notice how the forecast, red dashed line, closely follows the trend of actual demand, demonstrating improved fit without manual tuning. This visual confirms that optimizing alpha algorithmically can yield accurate, reliable forecasts efficiently. Error handling example 1, checking for missing dates. In real retail data, missing dates can break rolling forecasts. Let us identify any missing dates in our process sales time series. Running the cell now. Business time series must have consecutive daily entries, or forecasts will contain nouns or errors. Create a range of all possible days from the start to the end of the dataset. Find dates in the full range that are missing from our sales data. Print any missing dates so we can decide how to fill or correct them for valid modeling. Running the cell now. This output shows that there are no missing dates in the sales time series, as indicated by the empty date time index. This confirms the data is continuous and ready for reliable rolling forecasts, aligning with our goal to detect gaps that could disrupt time-based analyses. Error handling example 2, handling out of order or duplicated entries. Sometimes time series are not sorted, or have duplicate entries. Let us make sure our series is strictly increasing and aggregate duplicates. Running the cell now. Unsorted or duplicated timestamps can cause moving average and smoothing models to break. Group by each date and sum all sales, in case duplicates exist for a day. Sort by date so that rolling calculations work in time order. Show the first few values to validate our cleaned, sorted series. Running the cell now. This output shows the daily sales after sorting the dates and summing any duplicate entries, ensuring the index is strictly increasing. Notice the smooth progression of dates with no gaps or repeats, and the aggregated sales values that combine any duplicate invoices. This confirms the code successfully cleans the time series data for accurate, chronological analysis. Error handling example 3, misinterpreting lead times. If lead times are not considered, forecasts may suggest orders that arrive too late. Always align your forecast time horizon with operational lead times. Running the cell now. We adjust the forecast by shifting it forward to model a real-world 3-day supplier lead time. Set a variable for lead time, here 3 days, meaning that orders take 3 days to arrive. Adjust our forecast to predict demand 3 days in advance. Announce in output that we are showing a lead time adjusted forecast. Print the first 10 values so we can see the delayed effect in the series. Running the cell now. Here, the forecast is shifted forward by 3 days to simulate the lead time, resulting in the first 9 days showing NaN values because there is no data to forecast that far ahead. Notice how this aligns the forecast with the actual time when orders would arrive, emphasizing the importance of considering lead times to avoid planning based on unattainable delivery dates. This adjustment ensures that operational decisions are made with realistic timing. How would forecast error increase if lead time was a week or a month? Best practice, resample and aggregate for KPI reporting. Always aggregate operational data to the correct time unit for the business question. Let us create a monthly report of total sales and use it for KPI calculation. Running the cell now. KPI and operations metrics should use monthly or quarterly aggregation for a clear, strategic view. Resample the daily sales to monthly periods and sum the sales in each period. Display the first few months to confirm correct totalization of sales. These values will serve as the basis for downstream KPIs. Running the cell now. This output shows monthly total sales aggregated from daily data, with each row representing the sum of sales for that calendar month. Notice how the sales values vary month to month, reflecting real business fluctuations. This aggregation to a monthly frequency is key for accurate KPI reporting, as it aligns the data with typical business periods and decision timelines. Growth metrics allow business teams to monitor trends and respond to changes in market demand. Calculate the percentage change in sales from one month to the next. Replace missing first value with 0 for clean output. Label the output as growth rates in % to match business conventions. Print the rounded results for executive reporting. Running the cell now. This output shows the monthly percentage growth rates of total sales, calculated using % change on the resampled monthly data. Notice the volatility with large positive and negative spikes, reflecting rapid shifts in demand from month to month. This KPI highlights how aggregating correctly to a monthly level allows for meaningful tracking of sales trends critical for business decision-making. Best practice: align data for time series models. The order and spacing of your sales data must be correct for moving average and smoothing models. Confirm no missing time steps, and handle special events, such as close days, explicitly. Running the cell now. Handling store closures or holidays is key for realistic demand planning. Define Christmas Day and check if it is included in our time series. If the holiday is missing, insert a row with 0 sales for closure. Resort and re-index the series to restore proper daily frequency. Print actual sales around the holiday to demonstrate explicit handling. Running the cell now. This output shows the daily sales for December 24 to 26, 2010, with zeros explicitly filled in for both the original day and the inserted holiday on December 25. Notice the consistent daily frequency and no missing dates, which is crucial for time series models to correctly apply moving averages and smoothing without gaps. This confirms the data is properly aligned and missing special event days are handled as intended. If your business closes for multiple holidays, build a list and fill sales accordingly. End-to-end supply chain example: forecast, order, and report. Let us put it all together: forecast, create a batch order plan, and produce a monthly KPI report. We will simulate a demand forecast, translate to operational orders, then compute service level. Running the cell now. Here, we use an automated exponential smoothing forecast to build weekly orders and measure fulfillment service level. Create an optimized exponential smoothing forecast with no manual intervention and shift for true prediction. Sum daily forecasted sales for each week and round to nearest integer to simulate placed batch orders. Aggregate actual sales per week for a realistic operational benchmark. Combine forecasts and observed demand into a single data frame for evaluation. Received sales, met demand, is the minimum of ordered and actual sold units each week. Service level is calculated as the fraction of demand met by available stock, divide met demand by actual QTY. Show the first few results, giving an overview of weekly operational performance. Running the cell now. This output shows the weekly order quantities generated from the forecast alongside actual weekly sales, highlighting how many units of demand were met. Notice that when actual demand is non-zero, the service level is 1.0, indicating full service, while 0 actual demand results in a NaN service level. This demonstrates the key step of translating forecast data into operational orders and evaluating their effectiveness in meeting real demand. A high average service level means the supply chain met customer demand with minimal shortages. Assign each week to its calendar month so we can roll up performance for reporting. Calculate the average service level across all weeks in each month. Label the printout for management clarity. Show how service level changes over the course of the year for supply chain review. Running the cell now. This output shows the average service level per month, calculated by grouping orders by month and averaging their service level values. Notice the variation in service level trends, with some months at perfect service, 1.0, and others dipping below 0.8, indicating fluctuating order fulfillment performance over time. This KPI report helps assess how well the supply chain meets demand month to month, directly reflecting the impact of the forecast and ordering strategy. What would you recommend if service level falls below 95% for 2 months in a row? To see more on real-world supply chain forecasting, visit the YouTube channel linked in the notebook.